So hello everybody, thanks very much for asking me to speak at the forum. I know I've spoken to some of you before at other meetings, and this time I've been asked to talk about the UK Exascale project and also provide a bit of an update on EPCC and the Catalyst project we've been involved in, as some of you know, for the last couple of years. So in terms of a general EPCC update, the new national service Archer 2 has mostly arrived. I'll talk about that in a minute. We did a big upgrade to our Tier 2 system with a lot of GPUs last year in the summer, which is going well. And recently we've started to take delivery of a large Atos Sequana XH2000 system, which is the new DRAC extreme scaling service for particle physics and astronomy research. So that's just beginning to arrive now and will be operational in the next few months. We've also had our new computer room delivered. I'll talk about that. And we've also made a huge amount of progress with the Edinburgh International Data Facility, which I'll also talk about. So without further ado, I'll just move on. Oh, there we go. So I wanted to start by talking a little bit about the Edinburgh International Data Facility, and this is a 10-year project to provide a large data facility focused on driving data-driven innovation in southern Scotland, where Edinburgh is obviously based and EPCC is based. It's associated with a significant investment from the government, so there's about £110 million over that 10-year period, and it consists of this big IT infrastructure we're building, plus the new computer room and money to run the systems, etc., etc. In fact, on top of the 110 million, the 110 million is all capital funding. So what you can see on the left here is that the main part of the data facility is a big virtual cloud infrastructure. It can link to all the commercial clouds quite happily. At the top, we already run a number of what we call data safe haven services. I think these exist worldwide in a number of countries now. And this is where we keep data that is personal data, for example, health data and other data that needs to be stored in a particular way and has particular controls placed in it by the data controllers. And we run a number of data safe havens nowadays, including the Scottish government's national safe haven for health data, and other safe havens, for example, which store financial data for the banks, etc., etc. So that's a big activity for us, and the EIDF infrastructure and investments allowed us to add new features to it. For example, we've now put a Superdome Flex inside the safe haven, which is very useful for large data problems, large memory problems. And then the bulk of the projects which don't use controlled data are in the data science cloud service area below. That's very, very similar, in fact, in terms of the hardware to the data safe haven, but we've also added a Cerebras CS1, and I'll talk about that in a moment in more detail. Now, on the storage side, you can see we're using hierarchical storage. We're using HPE's DMF product. So we've got fast storage provided by the cluster store system. And then below, we've also got a large Ceph instance or instances in future, and then block storage as well. And this is the block storage is predominantly used, obviously, with the VM, with the virtual machines. So all of this is being put together at the moment. There's a new data center network we've put in, which is 200 gig Ethernet throughout the data center. And then we've also, for the first time, bought a firewall that covers the whole center. It's pretty expensive. It's operates at the line rate we have coming in. So the incoming line rate now is 2 times 100 gigabits coming from the UK academic network. And this, we're really massively increasing the amount of bandwidth into the site, which has been running at between 10 and 20 gigabits for a number of years. So I mentioned the Cerebras CS1. I think we've installed Europe's first CS1. It arrived in March 2021. It's just become operational now. These are really, really interesting devices. They're based around this one very large wafer scale processor, which you can see on the right here, the gold thing. It's 21 centimeters by 21 centimeters with 400,000 small AI cores. 1.2 trillion transistors. And I've really bought this for the data facility because Edinburgh's got this big focus on deep learning, and the CS1 gives us a capability that I think is unmatched in terms of a single device that can do these really, really large training problems. And we fronted it with a Superdome Flex with 1.2 terabits of networking between it and the CS1. So that's really exciting. We've got the first project starting on that at the moment. Archer 2 is somewhat of a challenge, to be quite honest. It was supposed to be delivered in February 2020. The first 4 cabinets, an HP Cray Shasta system, arrived in summer 2020. And at that time, or shortly thereafter, we finally turned off Archer after 8 years of operation. The first 4 cabinets provide 131,000 cores. Archer was 118,000. So there's basically the 4 cabinets are direct replacement for Archer. But in the final configuration, we'll have 23 cabinets. And the system will be just under 750,000 cores. So it's a big step up for us. We've had lots of issues getting the system installed. I think it's the first really large Cray Shasta system worldwide, but we are now making progress. So the remaining 19 cabinets were delivered recently, and we're hoping to put the 4 cabinet system and the 19 cabinet system together over the next month or so, hopefully with the system finally being accepted in June. But it's been quite a challenge, to be quite honest, but we are looking forward finally to getting the system working. You can see here, this is day 4 of the installation. These are really, really big installations. If you look at the racks, we have basically 3 rows of 8 racks. And in each row, you're basically looking at 250,000 cores. So it's significant infrastructure investment and really quite complex. So before I talk about the UK Exascale project, I was asked to also update on the Catalyst UK program. I'm not sure how many of you know about this. It was a collaboration started about 2 years ago now by Hewlett-Packard Enterprise, ARM and SUSE, and then 3 universities in the UK, EPCC at the University of Edinburgh, the University of Bristol and the University of Leicester. And the 3 sites each received a 2-rack large ARM-based system from Hewlett-Packard, and we've been working with the companies to demonstrate that ARM can be used very effectively for supercomputing applications and do a whole load of work around the system side of things on them and also the application side. So I could give you a very long talk on this. I won't. I'm just going to give you some highlight slides. But it's been a really, really interesting process, and we've learned a huge amount. And it's actually been very interesting, particularly in terms of informing what we might do later on at the Exascale. We're going to keep running the systems for at least another year because we're still finding them very useful, to be quite honest. So each of the systems is pretty much the same. They're all based around this HP Apollo 70 platform. They consist of 64 nodes, 4,096 cores per cluster and 2 racks. And they're based on the Marvell ThunderX2 CPU, so 32 cores per CPU, dual socket nodes, and 128 gig of memory per node, and Mellanox EDR InfiniBand connecting everything together. So other than the fact these are large ARM-based systems, very, very similar to what many of us have as sort of mid-range supercomputers in our data centers. Now, our system's called Fulham, and I always like to tell this particular story. So we named it after a lady, a Scottish chemist called Elizabeth Fulham from the 18th century, who very unusually in those days, because most scientists were men, published a paper herself, which is an essay on combustion with a view to a new art of dyeing and painting. But in fact, she described for the very first time the process of catalysis. So we thought with a catalyst system, naming the system Fulham was a nice thing to do. The main work on the system has been, as I said, to port applications, to test various different system software options, to measure performance, and also obviously to report bugs and collaborate with HPE and SUSE and ARM on resolving them. So the original setup we got, which worked straight out the box, was running SLES version 12 with the SP3 service pack, PBS Pro as the resource manager, and then a small NFS storage system, which was a mix of SSD and hard disk. That all worked very well, but we decided early on that having used it for the first paper, we wanted to make some changes. So this is the first paper that we put together. It was published very early on after getting the system in June 2019 at PASC 19. And we looked at the performance comparison of a range of applications on up to 32 nodes. You can obviously find the paper online. But having done that paper, we realized there were a number of drawbacks in the original setup. So we really wanted Slurm rather than PBS, because we're basically focusing on Slurm these days. We wanted to demonstrate Lustre storage, which Lustre wasn't supported by that version of SLES on ARM. And with the Lustre storage, we wanted to do both. We wanted to do the client running on Lustre, but we also wanted to do Lustre running on ARM as well, the actual the back-end system. And then we also wanted to make use of frequency scaling and turbo states, and that wasn't supported on SLES 12. So we decided to upgrade, and we decided to upgrade to SLES 15, which in theory supported all of the above. But I have to say, we then spent a huge amount of time making things work, particularly with regard to Lustre, which was a real struggle. And I think of all the different pieces of work we've done in Catalyst, that's been the most difficult. And it does point to the fact that ARM today, if it's going to be used as your primary platform in this way, you do need to consider that you're going to have to put some effort, or more effort is going to have to be put into making Lustre work well when you're doing ARM on both the Lustre storage itself and running the clients on ARM. So just as an example, here's the CAS-STEP computational chemistry code. You can see these results here are looking at frequency scaling. This is after we did the upgrade to SLES 15. And you can see that you might expect that as you increase the frequency, you just continuously get performance gains. But what you see in this slide very, very clearly is that you've basically got quite linear scaling as you increase the CPU frequency up to about 1.8 gigahertz. And then it just completely tails off. So, what you learn from this is, for this particular application running on this particular system, you've almost certainly here used either all the memory bandwidth or all of the interconnect bandwidth. And there's just simply no point in running your CPU harder than, say, 1.8, 1.9 gigahertz. You're just paying for energy to clock the system faster that you don't need to be paying for. And we also see this in some of the MEM-turbo settings. So MEM-turbo is a setting that you can either be off or on. And what you see when it's off is that the memory subsystem frequency tends to track the CPU max frequency. If you turn it on, an interesting thing happens. You limit suddenly the maximum CPU frequency to 2.2 gigahertz, but the memory subsystem frequency is now fixed at 2.3 gigahertz. So if you have a code that is memory bandwidth limited, you can tune, if you turn MEM-turbo on, you can tune your CPU frequency from 2.2 gigahertz and down in order to get the best performance related to the amount of you want to spend in terms of energy to power the CPU. So, and vice versa, in terms of you want to, if you're not memory bandwidth limited, but you are CPU frequency limited, then you probably want to play around on the other side of this particular coin. And we did lots of work on this, and you can see some of the results in the graphs below. And then finally, this final slide really just looks at how the compilers have evolved. So this is version 19 of the ARM compiler, and OpenMPI, and version 20. And you can see here that between these two versions, you're getting quite significant HPCG improvements, and we've really had a good experience with the ARM compiler, and we've tried a number of different compilers along the way. So moving now to the Exascale, most of you will, I hope, have noticed the recent Euro HPC announcements, or the announcements that happened last year now. So Finland's obviously going to be installing Lumi, which is a really significant system, 550 petaflops, supplied by HPE, based around the AMD EPIC CPUs and AMD GPUs that are just coming out now. And then Cinica in Italy is going to host Leonardo. That's supplied by Atos, and that's based around Intel Ice Lake CPUs plus NVIDIA A100s. So both these systems are really impressive, with the Italy Cinica's system just coming in at just under 250 petaflops. And there may well be a Spanish announcement in the near future. So with that in mind, that focuses mine somewhat. And it's clear the UK needs to have an Exascale project strategy. And I talked about it before we all went into lockdown. In 2019, when we had the HPC User Forum meeting in Edinburgh, I spoke at some length about the UK Exascale project. And I thought it would be useful to update people on where we are with that now. So since February 2020, I've worked 1 day a week for the government, for the UK government, as Director of Research Computing for the Engineering and Physical Sciences Research Council. I'm doing a number of things in that role, but one of them is to help to develop the funding case for an Exascale system in the UK. The UK supercomputing science case was completed in 2020. That was led by Mark Wilkinson, who many of you will know. And within UKRI, we're now taking the draft business case that was produced in 2019 and editing it, improving it, and thinking about taking it to government for funding in autumn 2021. And in truth, there's a very fixed timeline when you begin to actually work out exactly everything you need to do. So the planned service opening is now April 2024. And with as you work back from that, you know that you've got to have the hosting environment ready by the middle of 2023, which means you've got to procure the system in 2022, so it can be manufactured and installed in 2023 and the early part of 24. But it also means you've got to make all the changes to your hosting environment probably during 2022. There are a number of specific requirements from government around this. It should support both traditional modeling and simulation and AI deep learning applications. It should be available to both the scientific user community in the UK and industry users, probably with an 80-20 split. We should have specific support programs around SMEs. We need to have a software program. And although we were initially targeting 2023 for operation, it's now been agreed that a more realistic target is 2024. With all of this in mind, I've continued to develop the data center that the system will be hosted in. So this is the Advanced Computing Facility at the ACF. I think I spoke last time about the fact that we were building a new computer room, and you can see the design here on the right for that. This is on the bottom here, you can see the existing data center. We've now built computer room 4 on the right, in the middle of the page here. At the same time, we're installing a new 30 MVA substation. So that's two 30 MVA wires in resilient fashion, which are going to deliver up to 30 megawatts of power to an Exascale system, which will be hosted in computer room 4. I know it says phase 4 Exascale there on the plan, but we think probably that we can fit an Exascale system into the room that we've built. So here you can see the room. At the moment, there is transformers and cooling for 6 megawatts. So the next piece of development we're going to do with the system is, with the room, is to plan all of the extra cooling that's and electricity distribution that's needed once the new power supply comes in. And that's really quite a significant undertaking, but it's all been planned for in terms of our design. So though we built the room as a 6 to 8 megawatt room, it was designed to be able to host up to 30 megawatts of supercomputing. So here you can see the building. We accepted it in December, and it's already performing really, really well. We're still thinking very hard about what different technologies we should be looking at in the UK for the system. And if you look here, I think this is a really important slide, because if you look at the K computer, and I've taken the HPCG results from June 2019 before K computer was turned off, and June 2020 after Fugaku was entered the HPCG benchmarks. You can see that, you know, 8 years after it began, the K computer would still have been 22nd in the top 500, but it would actually have been 5th in the HPCG results. If you look at Summit, yes, it's got a big R peak of 200, an R max of 148. So you're getting an R max to R peak fraction of 74%. But its HPCG fraction is really, really not that great, 1.97%. But look at Fugaku, and in fact, look at the K computer. The K computer, the reason it's still high up in HPCG is because it manages a 5.73% fraction of R max. With Fugaku, it manages an HPL R max of 415 petaflops. But its R max to R peak ratio is very similar to that of Summit. But look at the fantastic HPCG result. I think this does argue that there's a lot to be said for the Japanese model. I think probably what we're going to do in the UK is go for a model where we have a large part of the system which is cores only, and a large, significant part of the system that is GPU and cores. But of course, there's a lot of water to go under the bridge until we run and conclude our procurement. So I think many of you will see what's happening at the moment. You know, obviously there are all these designs with a CPU at the center of a system, of a node with various GPUs around it. It is a really interesting moment in time. So we've got much more competition in CPUs and GPUs at the moment. ARM is definitely a significant threat to both Intel and AMD. And AMD is really strongly competing with NVIDIA in the GPU market. Cabinet energy densities are continuing to rocket. And I think it's just a very, very exciting moment in time. The other thing I want to say is we're still aiming to create the heat battery I've talked about in the past. So this is the mine workings underneath the data center. On the right-hand side, you can see the southern part of Edinburgh. And what we hope to do is use the cold water in the mines to warm that up using a surface heat exchanger, and then for that heat to be taken out to heat homes and businesses in the southern part of Edinburgh. And we're pressing ahead with this model at the moment. It's all part of our net zero plans. We're already on 100% green electricity at the data center. So I wanted to cover off a final question from Hyperion, which was, I was asked to comment on. So the question I got was, exascale computers are very expensive. What happens if the UK doesn't fund this effort? Which is a good question. And the truth is, you know, obviously I'd be quite sad that we don't achieve an exascale system before 2025, but Archer 2 will need to be replaced in 2025. So the simple fact is that its successor would simply not be an exascale system. It would be a large supercomputer, but it wouldn't be an exascale system. But I'd argue that it would have knock-on, a decision like that would have knock-on effects for UK scientific and industrial research. There are absolutely clear economic benefits of an exascale investment. We've shown that in our economic case to government. UK science that wanted to do the biggest and the best science would have to apply for limited access to resources overseas and wouldn't, in many cases, be able to get access to any of those resources at all. And many UK companies wouldn't have any access because of data security and other issues like export controls on their data. You know, and my argument and my challenge always is that surely the world's 6th largest economy should be investing in the future and should be investing in technologies like exascale. And with that polemic at the end, I'd like to thank you very much for your attention and ask if anybody has any questions. Thank you very much.